Okay, we're going to learn about a pretty abstract theorem here. It's called Rolle's theorem. So Rolle's theorem says, suppose that y equals f of x is continuous at every point on the closed interval from a to b, and is differentiable at every point of a to b. If f of a equals f of b, then there is at least one number c in a to b at which f prime of x equals 0. So let's kind of break that down. So first of all, we're saying we have a function that's continuous and differentiable, at least on our interval. Okay, then this part is saying that f of a equals f of b. Now what does that mean? That means the y values at a and b are equal. Okay, then we're saying there's at least some number in between there where the derivative there, we're saying f prime of c is equal to 0. Okay, so let's think of what that means. So we have some a and b, and we know their y values are the same. It doesn't matter what they are, but they're the same. Now, there's kind of three possibilities of what could happen between a and b since it's continuous and differentiable. So we don't have any jumps, we don't have any holes, we don't have any cusps or asymptotes. So if we started by going up, well, to get back to where that other point is, we'd have to come down. And at the maximum point, we'd have a horizontal asymptote. The derivative would be 0. Okay, so second possibility, well, if it started going down, it'd have to come back up to get to that point. We have a minimum where the derivative would be equal to 0. So, this value right here would be our c. Here it would be our c. Okay. Now, the one other option, if it didn't go up or down, it would stay the same. And there, since it's a constant, the whole thing would be, the derivative would be 0. Now, it's important to note that this isn't telling us how to find the value c, it's just telling us that it has to exist. So here's one way that we can use Rolle's theorem. So it says, show that f of x equals x cubed plus 4 over x squared plus 7 has exactly 1 0 on the interval from negative infinity to 0. Okay? So the first thing we could do is try to find where that is equal to 0. If we try to find where is x cubed plus 4 over x squared plus 7 equal to 0, first thing we could do is multiply everything through by x squared. That would give us x to the 5th plus 4 plus 7x squared equals 0. So x to the 5th plus 7x squared plus 4 equals 0. There's not an easy way to solve this. So let's go ahead and put that into our y equals. So x to the 5th plus 7x squared plus 4. Now where it's equal to 0 would be the same as an x-intercept. Okay, and we see we do have one here. It looks like it's at negative 2. Let's go to our table and say if we put in negative 2, we do get out 0. So we can say that this function f of x has a 0 at x equals negative 2. Now we're not quite done because this says show that it has exactly 1. And so we showed it has 1, but we need to make sure it doesn't have another 1. Okay? Or any more. So to show, we're going to have to do a little proof to prove that it can't have any more zeros. So this is actually going to be what's called a proof by contradiction. We're going to assume that there is another 0 and show that that contradicts Rolle's theorem. Okay, so we're going to say assume there is another 0. Okay, and we'll say at x equals b. Then here, let's say x equals a, just to kind of keep it. So that would mean that f of a equals 0 and f of negative 2 equals 0. So we'd say, so by Rolle's theorem, there must be an x value c between a and negative 2, where f prime of c equals 0. Now let's take the derivative. F prime of x is going to be equal to 3x squared minus 8 over x cubed. Okay? And what we need to see is that this is never equal to 0. If we try to set this equal to 0, or if we look at our, so if we set this equal to 0, we'd get 3x to the 5th minus 8 equals 0, so x to the 5th equals 8/3. So the only place where this is 0 is at the 5th root of 8/3, which is a positive value. And we're saying this happens somewhere on a negative value. So since f prime of x is never equal to 0 on the interval negative infinity to negative 2, or even 0, having 2 zeros would contradict Rolle's theorem. So we'd say, therefore, we can't have 2 zeros. Okay, so all we did here was use say, we know Rolle's theorem is true. It always has to be true. And if this had 2 zeros, then Rolle's theorem wouldn't work. But since we know Rolle's theorem has to be true, the assumption that we made that there were 2 zeros has to be false.